Okay, so just really quickly, I just want to say one other thing. On the last test, I got a phone call from the testing center, and I have no idea who the student is, so it doesn't matter. You can be guilty or you cannot be guilty. I said it wasn't a big deal. But somebody was going through the Excel help to try to figure out how to do a problem, I guess. The funny thing is I gave you guys all of the formula, all the commands that you needed on the formula sheet. It was there. So there was no reason to go to Excel help. So my response was, this person doesn't know what they're doing anyway. They're going to do poorly anyway. It doesn't matter. Okay? So I don't know if they spoke to you or not, but if you're going through the help during the test, number one, you shouldn't be doing that because you should already know it. And number two, I gave you the formula right there. Okay? So what are you doing? Okay? So anyway, I'll try to make that more clear. Like I said, I didn't make a big deal out of it, but yeah. If you're going through the Excel help on the test because you haven't done it enough, you should be able to look at that command and know how to do it. It was on the formula. Anything you needed was on the formula sheet, plus stuff you didn't need was on the formula sheet. But anyway, so once again, we've got to do our homework with quality. You know, if you're just saying, oh, I looked at it, I tried every problem, and I got 100%, and then you get a 50% on the test, that's the discrepancy, okay? So if you don't understand something, please get with me. My phone number is on the syllabus. You can text me. Remember, I'm teaching 5 statistics class, so don't tell me you're in my stats class. That doesn't help me, okay? Say, I'm in this class, my name is blah, blah. Can we meet at whenever? Now, just FYI, this week I'm free. Next week I'm gonna be busy in the evenings. I have 3 jazz camps next week. And I'm actually I'm going to Dodger Stadium this weekend. USC, UCLA baseball. All right, anyway. So if I can help you, I will, but I am busy too, so. All right, so we're gonna talk about chapter 13. And it's the uniform and the normal distribution, okay? Now, I know some of you have already turned in your homework, your 5 questions, because I posted this early as I'm trying to do better. I won't promise you I will do better, but I'm trying to do better. I hope that you put in some math problems, not definitions. If you already turned it in and it's only definitions, put some math problems in there. I want you to be able to calculate something with or without a calculator. Probably with a calculator would be a better problem. If you can do that, so if you already submitted and it was only definitions, please resubmit it. I haven't looked at it, but you should have a minimum of 3 math problems where you actually have to calculate something. All right, so let's talk about the uniform distribution. Yes. Okay? So what that means is the random variable x can take any value between 2 values. Okay. Did we talk about discrete and continuous earlier? Okay. Remind me, what does discrete mean? Discrete and continuous. Okay. So what did you say, Elizabeth?
Just a whole number.
The discrete are whole numbers, and continuous are everything else. Everything else. Okay. So the idea with a uniform random variable. Now, here's the thing. I always tell my students, most of chapter 13 is going to be on, we're going to talk about the normal distribution. The uniform is so easy that some of you are going to forget it, and you're going to just think normal because we're going to talk about normal a lot. Don't forget the uniform. It's super easy. Don't forget it, okay? So the idea, let's do an example. I actually had an eraser in my car, but of course I left it there. Oh well. Okay, an example. You have a friend that is always late up to 30 minutes. How many of you have a friend like that? Yeah, my wife has one too. She drives me crazy. I'm like, why do you keep that friend? Anyway. It's a she, but I'm going to say it's a he. He is just as likely to be 3 to 4 minutes late as 25 to 26 minutes late. Okay. So we're going to assume a uniform distribution. Now the funny thing is, I'm going to put uniform distribution on the test, and some of you are going to blow right past that and go straight to normal, because we're going to use normal a lot. Okay? So pay attention. Uniform does not mean normal. Okay? All right. So what is the probability? It will be between 10 to 20 minutes late. Okay? Now, have I introduced to you the phrase WWRD?
No.
Okay, you're probably all familiar with WWJD, right? What's that one? What would Jesus do? Okay, what WWRD? What would Rick do? Okay, that's what it means. Okay, and the answer to that question is always Rick would draw a picture. Okay, some of you do not like to draw pictures because apparently you like to get these problems wrong. Okay, I'm telling you, I will give you a point if you draw a picture, even if it's wrong. Hopefully it's right though. Okay, please draw a picture. So here's the idea: we've got a uniform distribution here. Okay, uniform distribution is always a rectangle. Always, always, always. Okay? Now, according to my problem here, your friend is always up to 30 minutes late. So what's the minimum this person can be late? 0. Okay? It doesn't happen very often. And up to 30 minutes. Okay? Now, if we think of this, what's the area of a rectangle? Length times width, right? Area is length times width, okay? Now, when we think of probabilities, what do the sum of all of your probabilities have to equal? 1, okay? So the area of this rectangle has to equal 1, right? Okay? So if this here, we're going to call this the length. If that length is what? The length is 30, and the area has to equal 1. How big is the width? 30 times what equals 1? 1 over 30. Okay? Okay, so this width is 1 out of 30. Does that make sense? Because the entire area has to equal 1 because it's probabilities, right? We're talking probabilities. Okay? Now, if this person is 10 to 20 minutes late, I want the area of this rectangle here. Okay? So how long is this?
10 minutes. 10 minutes.
That's 10? Yeah, 10 minutes. You can think of it as 10 minutes, right? And what's my width? 1 over 30. Okay? So my area equals 10 over 30, which is 1/3. Okay? So it's simply the area of that rectangle. Okay? Now, was that pretty easy? Okay? What's the probability that the person is 5 to 10 minutes late? Okay, so I'm going to pick on Jordan. Not this Jordan, but that Jordan. Okay? Jordan, how would you figure the probability that this person is 5 to 10 minutes late? I'll even use a different color if you want.
Okay. So using the first rectangle.
So 5 to 10, right?
Yeah.
So we'll color in this area here, right?
It's done at 30, right?
Yeah, still up to 30 minutes late. Same friend.
So it's 30 times,
30? Where are you getting the 30?
um,
What's the distance here? What's the length?
oh, it's mine.
5. And what's my width?
Is it 1 over 5?
1 over 30.
30.
Okay, remember, it's up to 30 minutes late.
Okay.
Okay? So this equals 5 goes into 30
6 times.
6 times. 1/6. Probability that this person is 5 to 10 minutes late is 1/6. Okay? Does that make sense? Yes.
So would you want those answers as a fraction or?
Yeah, leave them as a fraction. Yeah. So now let me ask you a trick question. What's the probability that they're 7 minutes late? Okay. Melina, what do you think? 7 minutes. I'm going to draw a picture here, right? Purple.
Just 7 minutes.
Exactly 7 minutes late. What's the length of 7? 7 to 7 is a length of 0, isn't it? It has no length. From 5 to 10 is a length of 5. From 7 to 7 is a length of 0. Times, what's your width? 1 over 30. The probability that they're exactly 7 minutes late is 0. Okay, there is no length. Now, just as an FYI, if you're talking about a continuous function, which we're going to talk mostly about, the probability of the x, here, I'll say it this way, the x equals any value equals 0, because it has no length. Okay? Yes.
Why would it be 0 and not like?
Okay, so let's do this. What's the probability that they're 7 to 8 minutes late? It's 1 times 1 over 30, which is 1 over 30, right? So anytime you have to do continuous, you need some sort of an interval. Okay? That's the probability that x equals any value is 0.
So is there another?
Because you know what? If you said they were 7 minutes late, you're probably rounding that. It's probably 7 minutes and 3 seconds late or something, or 7 minutes and whatever. Okay?
But if we're doing it as a discrete variable, is
We're
there
not
a way,
gonna.
is there a way to
So
do that?
here's your lucky thing.
Okay.
We're not gonna do discrete variables in this class. You can come to my Math 2040 if you want to do that.
So just think about this as
Okay.
continuous.
Now the probability that x equals 1, that could be a number, a value for discrete, but for a continuous, it's always 0. Okay? That's a good question, huh? Who's going to put that on their thing? Okay? Now, remember, that I'm only talking about continuous. It could equal a value with discrete, but we're not going to talk very much about discrete in this class. Okay? Yes, Emily.
Sorry, can you explain that to me just real quick one more? God was trying to help me, and it ain't working.
Okay, so you want me to explain the probability that any value is 0? Is that what you're asking me?
So, what did you say? Like the intervals. The intervals. I
Yeah,
guess,
so from 7 to 7. So remember, from 5 to 10, it's just 10 minus 5, right?
Yeah.
So from 7 to 7 is 0.
Oh.
So that's so you have a length. You have a length of 0 and you have a width of 1/30.
Okay. And I know that.
Okay? All right. Okay, so do you feel comfortable with the uniform distribution? Are you going to get these right on the homework and on the test? Okay, the rest of the semester, we're not going to talk very much about it. I will save it for the test, so don't forget it. But we're going to go to the normal distribution. All right. Oh, I can see that there. All right. So now, we're going to talk about the normal distribution. Okay? Oh, I didn't write this down, but somebody was going to, if I did write it down, somebody would put it as a test question. It's a terrible test question. But let me just tell you, just FYI, it was discovered by a guy by the name of de Gauss. Okay? It's actually called the Gauss, G-U-A-I, I don't know how to spell it, Gaussian distribution. Okay? Now, this is a funny story. Don't make this a test or a quiz question, but just telling you for, you Jeopardy lovers out there, he had a mathematical rival, and as you know, mathematical rivals don't like each other. Okay, did you guys know that?
That's why they're rivals.
And so the rival said, I'm not going to call it the Gaussian distribution because I don't like you. I'm going to call it the normal distribution because it's just normal. And it stuck. But the technical name is the Gaussian distribution. Now, FYI, you're all familiar with the bell curve, right? Okay. The equation for that thing is awful. Do you want to see it? Here, I'm going to give it to you.
Don't put it.
Y equals
Exactly.
1 over square root of 2 pi sigma squared e to the minus x minus mu squared over square root of 2 pi sigma squared. I'll make this a big E. dx. You take the integral from negative infinity to infinity, and you get a nice bell curve. Okay? You do not have to know that. I'm just going to. So don't make that a test question. Okay? So, and aren't you glad I'm not teaching you calculus? Because in order to do this, it's not like a nice little square here. That's why we started with the easy stuff. Okay? I'm not going to teach you calculus, but in order to do this, you really should use calculus. Okay? We're going to bypass the calculus, so don't you feel lucky. Okay? All right, aren't you glad I did not include that on the notes, so you didn't put that on the test question? Okay? That's just trivia. All right. So it is the most common type of data. Okay? And it can be used to simulate other distributions. Okay? We're not going to learn very many in this class. There's a lot of distributions out there. But we're not going to learn very many. But it can be used for exponential distributions, Poisson distributions. I'm just kind of giving you a bunch of names. T distributions, things like that. Okay? So some of the properties. These are good things to know. Okay? What do you think the area under the curve should equal?
1.
Should equal 1 or 100%, right? Okay? Just like with the uniform distribution. Number 2, the mean equals the median equals the mode. Okay? It's usually found here. We use the Greek letter mu. It looks like a U with a tail on the front side of it. Okay? Number 3, it is symmetric. Okay? We are going to learn a distribution that is not symmetric today, this semester. Not today, but we will learn it. Symmetry is a beautiful thing. When I teach you about this distribution that's not symmetric, you're going to be like, I don't like that. Okay? And the mean, mu, and the standard deviation completely define the curve. If I know the mu and I know the standard deviation, I can tell you a lot of really cool things. Now, one of the things I can tell you, for example, is what we call the 68, 95, 99.7 rule. Okay? Isn't that a great name for a rule? Okay? Some people call it the empirical rule. I like this name better, though. And I'll tell you why I like this name better. Yes?
Just a question. On the notes, it says 68.95 to 99.5. 99.7.
Well, mine says 99.7. You must have typed the 5 over the 7 or something. Yeah, it's 99.7 is what it should be. Okay? All right. So here's the deal. Okay? Rule number 1, 68% of your data are within 1 standard deviation. Okay? So the idea here is if I go out -1 sigma and +1 sigma, 68% of my data will be within this area here. Okay? If your data are normally distributed. Okay? Rule number 2. 95% of the data are within 2 standard deviations, right? But that was hard to figure out. Okay? So the idea is if I go out minus 2 sigma and positive 2 sigma, this area here under the curve is 95% of your data. Okay? And I'll bet that Greg can tell me rule number 3. You don't know? It's the 68, 95, 99.7 rule. You're not seeing a pattern there?
99.7%.
There we go. Melina's piping up for you there. 99.7% of your data are within 3 standard deviations. Okay, so if I go out here to minus 3 standard deviations, positive 3 standard deviations, this area here is 99.7% of your data. Does that make sense, Greg? See, why didn't you think of that sooner? Okay.
I'm trying to write down what you got.
All right. Okay, so let's do an example here. Ow, that hurt. All right. Okay, let's say that women 18 to 24 are 65 inches tall with standard deviation equal to 2.5 inches. So my question is, find the 68, 99, 95, 99.7 rule. Okay, and draw on a normal curve. We're assuming it's normally distributed. Okay, so it must be Henzie's turn, isn't it? Okay, so what would Rick do? He would draw a picture. Okay, draw a picture now of a bell curve, not a rectangle, because we're not dealing with the uniform distribution anymore. What's the mean, Henzie, of this bell curve? The mean mu equals 65 inches, right? Okay. Now, how tall are 68% of women?
Inches plus or minus 2.5 inches.
Okay, what Jordan said was correct. Can you give me the endpoints on that? Say it again, Jordan, she didn't hear you.
65 plus 2.5 inches and 65 minus 2.5 inches.
Okay, so 65 plus 2.5 is what, Henzie? Thank you, Greg. 67.5 inches, and 65 minus 2.5 is, Henzie? 62.5. That's close. Okay. Okay. So, by the way, they actually call these, if you want to be super smart, pass a Jeopardy question. Those are actually called points of inflection. Tell one of your calculus friends that you learned about points of inflection today, and they'll be very excited. Okay. Now, let's pick on Emily. Can you give me rule number 2, the endpoints for the 95?
What did you just ask for?
I want you to come up with rule number 2. What are these values here for the 95% rule? What's your standard deviation?
2.5.
2.5. So what do I do with that 2.5? I'm going to subtract it from here, right? What's 62.5 minus 2.5?
Oh, wow. 60.
60. And what's 67.5 plus 2.5?
70.
70. Very good. Okay. All right, and now, Ben, rule number 3 says what?
That 99.7.
99.7% of the data falls between 3 standard deviations. What are those values?
57.5 and
72 and a half. Okay. All right. Now, when I put this on the test, not if, but when I put this on the test, you know, I'll give you different numbers in here. How many of you are going to be able to draw me a normal curve with the 68, 95, 99 rule? On a piece of paper. Okay. Everybody's hand didn't raise. How come? Okay. This will be a test question. I've got it on video. Okay. Are you going to get it right? Okay. I just told you this is a test question. I'll give you different numbers though. Okay. This is a test question. It's super important. Okay. Don't miss it. Okay. Yes, Emily.
So I just want to make sure. So when you're subtracting on the left side, is it because it's like, are you thinking of it as negative?
Yeah, so just like I drew here, over here, on my board here. So one standard deviation has 68% of your data. Since my standard deviation here is 2.5, if I go up and down 2.5, I'm going to get 68% between those numbers. Okay? If I go 2 standard deviations, so in this case, 2 times 2.5 is 5. So plus or minus 5 from here, subtract 5, I get 60. I add 5, I get 70. Okay? And then 3 times that is 7.5. 57.5 to 72.5. Does that make sense? Okay, this will be a test question. Okay, don't forget. Great quiz question, but don't everybody put it on there. Okay? All right. Okay, so now the question arises, what if I asked you find the probability that a woman is between, say, 63 inches to 66 inches. Now, is the 68, 95, 99 rule going to help me with that? Okay, so what we have here, I think I'll go over here, is we're going to create what we call maybe I should have added a few more questions. I gave you a lot of homework, but I just remembered one I want to add. I'll give you some more homework. So we're going to talk about the standard normal distribution. Okay. Now, up to now, we've been talking about a normal distribution. I'm going to add the word standard normal distribution. Okay. Standard normal distribution is just like what we've been talking about with 2 special words. Number 1, it has the word standard in there. Some of you are going to blow past that. And I will say, what is the mean of the standard normal distribution? And you'll say, some of you will say, I don't know, you didn't tell me. And I will say, you should know that. The mean, mu, is always 0. Okay? The standard deviation, sigma, is always 1. Okay? Standard normal distribution is a special distribution. And the idea here is that any normal distribution can be converted to a standard normal distribution with the following equation. And the equation is z equals x minus mu over sigma. Okay? Now, you're going to do so many problems in here, you're probably going to memorize that. I'll give it to you anyway, but it's a really super useful formula. Put a big star by it. You're going to use this a lot. Okay? Now, here's what's cool. Okay? 68, 95, 99 rule is really cool if I happen to get one of these standard deviations exactly. But if I'm not, okay, like in this case, a 63 to 66, that's not one of my endpoints, right? So here's what I would do in this situation, because I say, what's the probability that a woman is between 63 and 66 inches? And your first thing you're going to say is to yourself, WWRD, right? Draw a picture. So you're going to draw a picture, okay? Unfortunately, I can't use the 68, 95, 99 rule, but I know that my mean is what, Jordan?
Mean is 0. Or no, for this one it's 65.
65 inches, okay? And I want between 63 and 66, so I want 63 to 66, right? I want this area here. Now, if this was a uniform distribution, what would I do? I would usually do length times width, right? This is a normal distribution, and I don't know calculus, right? Okay, so we're going to teach you how to do this without knowing calculus. Yes?
Can you explain to me how you got the 65?
Women are 65 inches tall with a standard deviation of 2.5. So that the mean is
I thought
65.
the mean was always 0.
The mean of the standard normal is always 0. This is a regular normal. It's not a standard normal.
Oh, okay.
Okay,
Well, you
but
specified-
we are going to convert this to a standard normal. So I'm going to convert this to a standard normal, and this is going to turn that mean from 65 inches into 0. And I've got to figure out how many standard deviations I'm away. So I'm going to find those two values. Okay, does that make sense? So you're going to the right place.
But will you specify that it's like we're going to do the normal distribution, not the standard? Like on a test?
Probably not. Okay, I'm going to expect that you're going to convert it yourself. That's what you're going to have to do.
What about, you said if it was a uniform distribution, we could do that way, but since it's,
If it was a uniform distribution, I'm going to draw a rectangle, and I'm just going to figure the area of the rectangle.
how do you know the difference?
Because I said it was a normal.
Oh, okay.
In this case, I said it was normal. Okay? So uniform, normal, standard, those all sound very like synonyms. They're not. Okay, so pay very close attention to those. Uniform is a rectangle. Standard, 0 and 1. Regular is just whatever this is, 68, 95, 99, okay? So yeah, you got to pay very close attention. All right. So what we're going to do is we're going to convert this to a standard normal distribution because I'm not going to teach you calculus today. Okay, I'm going to show you a cool table though. Okay, so here's what we're going to do. We're going to use this equation twice. Okay. Now, another way to think of this equation, x minus mu over sigma, you can think of this as data minus the mean over the standard deviation. Okay? So if you want to think of it that way, that will work. Okay? So here's what we're going to do. I've got two endpoints. I've got 63 and I've got 66. Okay? So I'm going to find the z-score twice. Okay? So z equals, I'm going to find it first for the 63, and I'm going to pick on Alex. Can you help me do that?
Sure.
Okay. If I'm starting with the 63, what's my x?
63.
63
Yep.
minus
And then minus 66.
60 what?
Would it be 66?
66 is 66 the mean?
Oh, fine, 65.
65 is the mean. And I'm going to divide that by 2.5. Very good. Okay, so 63 minus 65 is negative 2 divided by 2.5. That equals, who's got their calculator? Negative 0.8. Negative 0.8. Okay, so what we've just done is I've converted that 63. I am now negative 0.8 standard deviations away from the mean. Okay, now we're going to have John help us do this other one. Now we're going to do it for the 66. Okay?
Would be 66 minus 65 over 2.5.
Over 2.5. Okay? 66 minus 65 is 1 divided by 2.5. What does that equal? 0.4. Okay, so now I've converted this 66. I'm now 0.4 standard deviations away. So I've now converted this from a regular normal distribution to a standard normal distribution. Does that make sense? Yes.
What's the second equation with the 66 and 65 instead of 63?
So I just used this equation twice. I'm doing it for each endpoint. Okay? Because I want to know the area between those two. So I'm going to use those. So I'm going to use those two endpoints. Okay? Yes.
Is that equation standard or normal?
This equation converts any regular normal to a standard normal curve. So you're going to use this equation all over the homework. It's going to be probably your favorite one. The second favorite one's going to be length times width.
In that one, though, why is it not 1 or 0?
Why is what not 1 or 0?
Like the mean.
Because if
or
we're doing it-
The mean, yeah. So when I use this equation, it turns the mean to 0 and it turns the standard deviation to.
So that's the goal.
That's the goal. Yeah.
Got it.
Yeah. So now, yeah.
Sorry, what is the -0.8 and the 0.4 column? Like, are those the endpoints? Is that what?
So you remember the 68, 95, 99 rule here, okay? We know this. What we're trying to do is we're trying to convert it to a standard normal, and we're converting it. So we're now, instead of being 1 standard deviation away, I'm negative 0.8 standard deviations away on the low side. And on the high side, I'm 0.4 standard deviations away. So I would be about right here and about right there. So I'm trying to find this area here. Okay? All right, now, for those of you who have your computers, go ahead and open up Canvas. I shared this like on the first day of class. You probably did see on the last test, I gave you a lot more information than you needed, right? Because I didn't want to reprint this formula sheet over and over and over. So these are all the formulas you're going to need for this semester. Okay? Oh, I hate this thing. Okay. All right, so if you go here to stats, or if you go to announcements, it's probably in the book too, but I know if you go to the very first announcement, no? Tables and formula sheets, sorry, it's right here. February 20th is where it is. Okay, so I've got 2 formula sheets. So just as a reminder, download these. You're going to use these a lot from here on. So just as a reminder, here's your formula sheet. Okay. Got a lot of your formulas that we've already used. It's also got your population z-score. It's got your sample z-score. We haven't talked about that, but we will. Okay. So there's your formula there. It's got a bunch of other stuff. But what I want to do is open up the other document here. Okay, there's your random digit table. Now we've got here, this is what we're calling a normal distribution table, a standard normal distribution, okay? So here's the key, okay? So the idea here is, first of all, look at the picture here. You can see here that I've got a blue area. So what it's telling you is it's telling you everything that's to the left of whatever this red line is, okay? So here's what's going on. We got 2 z-scores. One of them was 0.8, negative 0.8, okay? And one of them was positive 0.4. Okay, so here's how you're going to use this. What this tells you is if you go down here to negative 0.8 right here. Okay, now each one of these is a decimal. So this is negative 0.80, negative 0.81, 0.82, etc. Okay, so I got negative 0.8. I'll put a 0 on here just for fun. So I'm going to be looking here at the first column. So what it's telling me is I've got about 21% of the area to the left of negative 0.8. So if I draw my picture here, just to make sure you're clear, okay, let's go over here. Okay, so what's going on here from, if this is a mean of 0, because we've converted this to a standard normal, I am now negative 0.8 standard deviations away. This area to the left is 0.2119. Does that make sense? Okay. Now we're going to do it again. This time we're going to do it with our 0.4. Okay. So if I go back to my table here, okay, I'm going to 0.4. Oh, I'm going to go a little bit lower. 0.4, that's going to give me this area here. Do you see that number there? So what this is telling me here, if I draw another standard normal curve, I've got a mean of 0. I am 0.4 standard deviations away. I've got this area here to the left is 0.6554. Okay, now, the area that I wanted, I'll just draw a new picture here. I wanted this area here, but I'll just redraw it here. The area that I want, purple to match, okay? I want the area between negative 0.8 and positive 0.4. I want this area here. I want to figure out what that area is. Okay, does that make sense? So given these two numbers, how do I find this area? Subtract them. I'm going to take 6554 and I'm going to subtract 2119. Okay, and that gives me, let's see if I can do this in my head. So this area here, 0.4 is 0.6554. This area here is 0.2119. I'm going to subtract them, and I'm going to get this area here, works out to be 14 minus 9 is 5, 4 minus 1 is 3, 5 minus 1 is 4, and 6 minus 2 is 4. Somebody check my math, but I believe that's correct. 0.4, so about 44% of women are 63 to 66 inches tall. Does that make sense? Yes.
So you take 0.6554 minus
0.22119. Okay? Yes.
So why did you only go over one? At one point, did you go over more points on that table?
Oh, that's a good question. Okay? So when do you go over more? Let's do another example. Okay, I tried to keep it simple. Okay, we're going to go hard now. But actually, before we do that, let me make sure I'm following my notes a little closer. Yes.
So does it matter? Sorry. Does it matter which one do you subtract? Does
The
it
bigger,
matter?
remember, you don't want your probability to ever be negative. So it's
I
going
just wanted
to
to
be,
make sure that
it's going to be the big number minus the small number as a general rule. Now, don't subtract these. Sometimes people subtract the z-scores. Don't subtract those. The reason why you can't do that is because this is a big curve. If you subtract these first, then you're in trouble. It doesn't work that way. Okay? All right. So, I'm going to pick a good one to kind of answer Emily's question a little bit better. Okay? Okay, so you're going to be using this table a lot. Now, we can also do this on the computer. We'll do that in a minute, okay? I'll show you how to do this on the computer. The computer works just like the table. But let me stop sharing here. We're going to do another example. Okay? Use my awesome eraser here. Okay, so this is a very useful thing for why this Z equation is awesome. Okay, let's say that the New York Yankees scored 968 runs in the American League. The mean was, oh, I made a mistake. Let me fix my mistake here. The mean was 793.9, and the standard deviation was 73.5. Philadelphia Phillies scored make sure I'm doing this right, 892 runs in the National League, with a mean equal to 763 runs and standard deviation equal to 58.9. Okay? Who did better versus their respective league? Okay? So now some of you are not baseball fans. Who's not a baseball fan? What is wrong with you? Okay? Actually, I should have picked the Red Sox, not the Yankees. I hate the Yankees. Okay? So for those of you who don't know, the American League has a designated hitter and the pitcher doesn't have to hit. Okay? So the American League always scores more runs because they've got more hitters. The National League always scores less runs. Okay? So the idea here is you don't want to compare, you can't compare them directly because they played under different rules. Okay? So the idea is who did better. And you can't just trust, well, 968 is greater than 892 because.
Rates are better than counts.
What's that?
Rates are better than counts.
Rates are better than counts. Very good. You can think of it that way. Yeah. Okay. All right. So the question is, what we want to do is we want to convert this to a standard normal curve. Okay. So then once we do that, we can compare them directly because the standard normal curve has a mean of 0 and a standard deviation of 1. Okay. Tell me your name. Sitting next to Penzie. McKenna. I should remember that. McKenna, are you a baseball fan? Kind of. Okay. So, can you help me find the Z-score for the Yankees? Z-score for the Yankees equals. Okay, and remember, it starts with X, not the mean. What's the X?
So 968.
968 minus the mean, which is 793.59, excuse me, divided by 73.5. Who can punch that in their calculator and tell me what that equals?
What's the little thing next to the D?
That's a Y for the Yankees. Just so that I can distinguish. Because I'm also going to do the Z for the Philadelphia Phillies. Okay? So who's got that value for me? 2.37. Okay, so make sure you're using your parentheses on that because you don't want to mess that up. Okay, so now I'm going to pick on, is it Amanda?
Yeah.
Oh, I got it right this time. I screwed it up last time. Amanda, can you help me do the Phillies? 892. 763 over 58.9. That equals what? 2.19. Okay. Now, WWRD. Draw a picture of what? Of a bell curve. Okay. Bell curve. So what's going on with my bell curve? What's the mean of my bell curve? John.
Why don't you draw the bell curve for each one?
You could, but we want to compare them directly. And if I draw them separately, then I can't really compare them. So the idea is I want to put them on the same curve. Okay. So what's the mean of my same curve? 0. Where are the Yankees? How far away are the Yankees from 0? They're 2.37 standard deviations, right? This is the Yankees. How far away are the Phillies? The Phillies are not as far, are they? They're 2.19. Okay, can you tell just by looking at the graph who's better? Huh? Who did better? The Yankees, because they have a higher score, right? Okay, now let's figure out what percentile are both teams. How would you figure that out? We can use our chart, right? Let's use our chart. Okay, so if I share my screen. So now this answers Elizabeth's question now finally. That was a long answer, huh?
Yeah.
Okay, so 2.37. Okay, so the idea here is, if I go down here to 2.37, so here's the problem because I can't really see the top, but just remember, just count over. So I'm at 2.30, right? So this is 0, 1, 2, 3, 4, 5, 6, 7. What value is that? Yeah, 0.9911. So what we're saying here is the Yankees did better than 0.9 or 99% of the teams, 0.99111. Okay? So the Yankees are in the 99th percentile. Okay? They did better than almost everybody. Okay? How did the Phillies do? Who can help me do this one? I'm going to pick on Hannah. 2.19, so 2.1 I'm on this row, 9 is all the way at the end, right? What percentile are they? Yes, 0.9857. So they did better than, in this case, where's my red? The Phillies did better than 0.9857% of teams. They're in the 98th percentile. So they both did really well, right? But the Yankees did a little bit better. Okay, does that make sense? Okay, now let me ask you a few more questions here. Oh, shoot. Am I any questions? I'll have to mix them up. Okay, let's okay, here, I'm going to keep this question for a minute. Okay, let's do this. Stop sharing. How many runs would you have to score to be in the 67th percentile in the National League? Okay, this is a good question. Any ideas how you do this one? Any favorite equations? Laura, what do you think? Do you have a favorite equation for this chapter?
Nope.
You don't? The one with the big star by it might be nice. Okay. All right. So our favorite equation is D equals x minus mu over sigma, right? Now we got to figure out how we're going to do this. Now, what do we know? We know the mu and we know the sigma, right? Okay, so I'm going to write those in here. The mu is what, Laura? For the National League? 763, and the sigma is 58.9. Okay. All right, now the 67th percentile, let's think about that for a minute. What we're going to do is we're actually going to use this chart backwards. Okay, so I'm going to share the chart again. Okay, now remember in blue here, these are my z-scores, and here is my area. Okay, so what I want to do is I want to find 67% or close to that. So 67%. So there's 69, 65, 66. Oh, look at that, 67%. That was right on the money. Usually you have to round it a little bit, okay? So what z-score is associated with 67%? 0.4, and then I go up to the top of this column here, 0.44. Do you see that? So this is 0.4, and then this is right here. I go up to the top of here, 0.44. Does that make sense? Okay, so I'm looking for the 67th percentile. So what did I skip that I should not have skipped? What would Rick do? He would draw a picture. What's going on here? Okay. If I'm in the 67th percentile, okay, do I want to shade the right side or the left side? I want the left side. Okay. I want this area to be 0.67, right? Okay. So the idea here is under the normal curve, the standard normal curve, what's the mean?
0.
The mean is 0. Okay. So what number corresponds to 67%? Okay, that's where I'm using my chart backwards. And what it's telling me is if I go 0.44 standard deviations away, 67% of the curve is to the left of that number, which means 33% is to the right. Does that make sense? Move the camera over.
Or like, I don't know. Are you, I can't tell.
Okay, so the idea here is I'm using this chart backwards, okay? So right here, do you see here, 67%? I highlighted it right there. Do you see that? Okay, so if I look right here,
Oh, sorry.
67% is
No,
right here.
I meant on the camera, on your,
So we can see it.
so we can see what you're doing with the board.
I'm sharing this. When you watch this at home, you're going to see this. You're going to see what I'm playing.
No, I mean on the whiteboard.
On the whiteboard.
Sorry.
You want me to show you the whiteboard?
That you're drawing right now.
No, I don't think it's recording on the whiteboard, like where you're writing.
Okay, so I want
No.
67%.
The camera's not on what you're writing. Like.
Oh, I see what you're saying. I need a cameraman. Okay. Okay, now I got it. Okay, thank you. Okay, thank you for being my camera man. Yeah, I just assume it's following me. Okay, so 67% is to the left. Okay, so that gives me 0.44. That's my z-score. Okay, so the idea here is I'm going to convert this z-score to the standard normal, to the regular normal for the Philadelphia Phillies in the National League has a mean of 793. The question is, what is that value? Okay, so I'm still going to use this equation here. Okay, now I know what my z-score is. What is my z-score? 0.44. And then I just need to know what the x is my data, right? That's what I'm looking for. Now I just have to do a tiny bit of algebra and I need to solve for x. How do I solve for x? What? Multiply both sides by 58.9, okay? And I'm going to add 763. Okay, so x equals whatever that value is. Okay, so I can use my calculator. My favorite calculator is Excel. Okay, so now I've got equals 58.9 times 0.44 plus, whoops, plus 763. Okay, so you would have to score 788.9 around, yeah, 788.9 runs. Obviously, that would round to 789. Okay, to be in the 67th percentile, you'd need to score 789 runs. Yes.
So does this chart substitute basically a couple of the steps out of that huge formula that you wrote down?
Say that again.
So does this chart substitute a couple of steps?
So this chart, yeah, what it does is you don't have to learn calculus. That's the calculus. Basically, they just created a table that did the calculus for you. You just have to look up the values on the chart. Okay? Yes.
So for this example, there was a perfect 67%.
Right.
If you have to round, where
Which way should you round?
So that's a really good question. So if it's like right smack dab in the middle, well, for example, let's look up 10% on the chart. So like 10%, it's right there, 0.1003. I don't think I'm sharing that. Let me share that. Okay, so in this case, if I was looking for 10% to the left, that's close enough to 10% there, so I would go with negative 1.28. Okay? If I were going, let's say I wanted 95%. 95%. Okay, so you can see these two values here, 0.9495 and 0.9505. You see 95% is right in the middle of that. So that would be a case where I'd probably split the difference. I'd say 1.645. Okay, so I'd split the difference. Generally kind of go with what's closest, but if it's right smack dab in the middle, you could, the top of those are a 4 and a 5, I remember because I saw that. So you're gonna, you can't see the bottom there, but anyway, there it is. Yeah, it's right smack dab in the middle. So yeah, if you want to kind of extrapolate a little bit, or if it's close enough, just round to the nearest one. Okay? So now, last question I want to ask. Let's go back. Oh, I erased it. Okay. Here's what I wanted to do. If I add, so the last thing I wanted to just mention here is, let's go. So remember that women were 62.5 inches tall, and the standard deviation was 2.5 inches. And what if I said, what percent of women are less than 60 inches tall? And I'm going to use the 68, 95, 99.7 rule. Is that on there? No, it's not quite on there. Okay. So let's draw a picture. Okay. Once again, if this is 62.5, right? And I want less than 60 inches tall, right? Okay. Now I know between 60 and 65, this is 68%, right? Okay. But the problem is I want to know what's less than. I don't want to know what's in between there, right? Now, if this is symmetric, let me ask you this. If I split this in half, how much is on this side?
50.
What? So this side here, I've got 50%, right? How much is just between 60 and 62.5? I've got 34% here, and I've got 34% here, right? So if I've got half less than here, so I can take the 50% minus the 34%, what's that area? That would be 16%. Okay? So you can use the 68, 95, 99 rule a few other ways as well. Okay? And I hope I gave you enough homework. I may throw up another one if I like it. All right, so quiz on Tuesday is going to be on chapter 13. And we'll see you all on Tuesday.